So I'm going to talk about something called Automotive Audio Bus, which me and my colleagues, we've been working on quite a lot in the last year. We never call it Automotive Audio Bus, we just call it A2B, or A2B. So before I start, just a bit about myself. Yeah, Linux, long time. I actually can't remember since when I installed it. Mostly doing mathematics until 2015. Then I moved to embedded. And since joining my current employer, Bang & Olufsen, I've mostly been doing kernel stuff. Bang & Olufsen, for those of you that don't know, is a hi-fi company. We make, I want to say, high-end speakers. They're quite expensive, but they also look good and sound good. Much to my surprise, actually, basically all of the complex speakers, they run Linux, and there's actually quite a lot of fun kernel work to be done there. And yeah, also preface, A2B is a registered trademark. I just put A2B everywhere. Cool. So agenda, just to explain what is A2B, because I think, I don't know, it has, if people show their hands, has anybody actually heard of A2B? 1, 2. Okay, yeah. People I talked to yesterday and my colleagues. Okay, that's great, because I really like A2B. I think it's great. And in fact, we've been using it at Bang & Olufsen for longer than even I've been there. But it's mostly been controlled through microcontroller code and using some vendor library from Analog Devices. But of course, since we're using Linux, then there's a good motivation to also get a proper driver model for that bus. So I'm going to start just by explaining roughly what it is, talk about some inner workings, talk about how, yeah, I have attempted to model it in Linux. I think first patch set was submitted last week. Yeah, arguably there are some things that can be improved, but that's what the mailing list is for, so I guess people will correct me. I'll talk a little bit about how you configure this bus, what it's used for, and then we'll look at a case study, which is the first place where we used A2B in Linux, which is a product of ours called Biosound Shape, which I'll have a picture of it soon. Yeah. And some future work and challenges and kind of open questions. So after this talk, maybe tomorrow or something, if you have any kind of input on that, then I would love to talk to you. Okay, so the diagram you see here, this is basically just a block diagram of an A2B chip. They are pretty small. They're like, yeah, I looked in the datasheet today, it's 5.7 by 5.7 millimeters, which is quite nice. They're also pretty cheap. I think it's like $1 on the bill of materials. The current generation that you can buy, these part numbers that I have here, you control them over I2C. And they have some peripheral functions, but the most interesting one is down here in the bottom left, which is a digital audio interface, I2S, TDM, and PDM for microphones. And these transceivers that you see, the A side and the B side, these are just unshielded twisted pair cables, and you basically take these chips and you daisy chain them together. So you have this line topology. So a typical use case is something like this. You have your SoC, hopefully running Linux in the future, and you hook it up to a terminal node, which in the system, which is known in the documentation as the main node. And then you have this daisy chain of A2B transceivers, A2B chips, B side to A side, B side to A side, B side to A side. And the cool thing here is that this unshielded twisted pair, pretty much the feature is that it propagates digital audio. So over this TDM interface, you can pump digital audio from your host into there. And then the A2B kind of chip fabric allows you to quite flexibly and arbitrarily route your audio samples into one of these other subordinate node transceivers, and then it gets played out into typically some other codec or something like that. You have also I2C, which is useful because most audio codecs, they are controlled over I2C as well. And you can have also other peripherals there. I mean, you get a whole, for each subordinate node, you get a whole I2C segment, which is independent of the others. So you can have EEPROMs, you can have whatever. We actually, yeah, in some of our designs, we put quite a lot behind them. Yeah, and you can have up to 10 of these nodes, subordinate nodes, plus a main node. And the cool thing here, I don't know if you can see in the small text, but the node-to-node cable length can be up to 15 meters, which is pretty cool. And the whole system length can be up to 40 meters. I think analog devices in their newer chips, they have increased even these parameters. So yeah. And you can kind of maybe see, if you're kind of into audio and stuff like that, why it's called Automotive Audio Bus, because there's probably quite a lot of good applications in a car. If you have your stereo system, you have amplifiers and speakers in the back, you want to send digital audio to them, and you want to present the samples synchronously. And that's kind of the cool feature about this as well, which is that all of these digital audio interfaces, their clocks are synchronized. So the host is meant to deliver a clock signal into the main node, and then A2B takes care of locking some internal PLLs across the whole system of main to subordinate nodes, such that all of your audio playback is in sync, which is great. Yeah, and it's also cool because you have bus power as well, so you actually don't need to even remotely power these downstream sections of your hardware. You can just source 1.8 or 3.3 volts from the A2B transceiver itself. I think you get 300 milliamps or something like that. Yeah, and yeah, you see, you get up to 32 channels of digital audio, which I think is also super. Just a quick interlude, because I don't know how many people here are actually into digital audio or codecs and Linux and stuff like that. We have a hand there. Is that a question, or? Okay, great. So this diagram hopefully makes sense to you. I hope it makes sense to everybody. You don't really need to know as such how this works, but whenever you see in this presentation I2S or TDM, I'm basically talking about this serial interface here. So you just have two chips, and you want to transmit digital audio between them. And here we're talking PCM digital audio, typically. And you just have a bit clock, you have a frame sync, which asserts itself for every sample period. And you have a TX or RX data lines, which, according to rising or falling edge on the bit clock, the ICs are going to sample the data value. TDM just stands for time division multiplexing, so I2S is just only for stereo audio, but you can just jack up the bit clock and just say, okay, well, after 32 bits, I have channel 2, after another 32 bits, I have channel 3, and so on and so forth. But both sides have to agree on this. There's no negotiation as such. And why am I talking about this, and why is this interesting? I think one of the main value propositions of A2B is that if you actually want to carry this signal over a long distance, then you basically get an antenna. And bit clocks, they can get pretty high. And this presents a lot of challenges for kind of certifying consumer-grade products, because you can't just have spurious emissions all over the place. So A2B solves the problem by doing some modulation on these twisted pairs in order to reduce the emissions. And our hardware engineers like it so much that they kind of start putting it everywhere in our new products. Okay. So yeah, this is just kind of summarizing what I'm saying. It's just, robust, flexible interconnect. You can use it between ICs on a single PCB, or you can also connect discrete PCBs together just using a unshielded twisted pair, which I think is also good. Yes. So why do we care about this, or why do I care about this? So about a year ago, we had the problem that we have this product called BioSound Shape, which is a speaker. It's not an art piece. Some people might think so. But as you can see, it actually gets pretty big. And this is actually a modular speaker. So you can go on our website, and you can kind of customize your shape setup. You can pick how many speaker drivers you want, choose an according number of amplifier units, and then some technician will come to your house and wire it up. And, well, this thing is kind of, the number of speakers is variable. You don't know exactly what the customer is going to have. And crucially, the distances are quite long. These units, unfortunately, we were supposed to have a demo, but we couldn't get a van. These units, there's cables running in between these hexagonal tiles. But these cables, they kind of snake around the perimeter of the hexagons. So actually, the cabling gets quite long, hence A2B. So actually, this product has been on the market for quite a long time before I joined the company. It used to be driven just by a microcontroller, but now we released a new product, which rather than having a microcontroller controller in the beginning, now you just insert a Linux box in the beginning. And that Linux box is using A2B to drive the system. More on this later. All right. So this is just kind of to give you an idea of how things are actually controlled. So we have this I2C target interface on the main node, and it responds on 2 addresses. And then you connect your nodes together. That's denoted by these zigzaggy lines. And of course, you then have these I2C controllers on the subordinate nodes, which you can use to set up your downstream codecs and other peripherals. And the question is how to actually communicate between the host and these subordinate nodes, because there's no direct I2C link. And the way it's done basically is that ADI, they say, okay, well, all of these nodes, they actually pretty much have the same register map. If you access through the first address, you're just going to talk with the main node register map. If you go through the secondary address, then depending on some registers that you have set up in the main node and possibly the subordinate node, you're going to access kind of by proxy the register map of the subordinate node, or possibly one of the peripherals behind one of the subordinate nodes' I2C controllers. The way that this is achieved is also transparent to the host, because A2B, the main node, will perform clock stretching, so that the I2C transfer is actually completed synchronously. And you can also get, if the target knacks the message, then you're actually just going to get a knack on the address 69 on the host. Okay, so I'm not too into the details of the data structure that flows between the nodes, but ADI, their documentation is pretty good, and I think it tells you most of what you want to know as a software developer. So the bus itself is synchronized according to this frame sync signal that I referred to earlier, and out of this you get a bit rate of about 50 megabits. The data itself, it takes the form of the so-called superframe. And the superframe is actually 2 parts. So in every sample period, the main node is going to generate what's called the synchronization control frame, SCF, and send that downstream to the first subordinate node. And the first subordinate node is going to inspect this, maybe modify it a little bit, and then send it downstream to the second subnode. And so on and so forth until it reaches the last subnode. And that last subnode will then complete the pop all of the data and then generate a response frame. And then the same procedure happens again where it starts sending it upstream. And in the meantime, the data gets modified and the nodes, they decide what they want to do with it. And the data inside, the crucial thing, if you refer back to this diagram, we have the TDM interface on the host, and we also have these TDM interfaces downstream. And basically, you're moving audio samples between these nodes. And you can move them both downstream and upstream. Downstream meaning from main towards last subordinate node, upstream meaning towards main. So I spent kind of ages making this diagram, and I really hope it makes sense. I suggest for just to quickly digest this, because probably we don't have that much time, the place you should really be looking is sort of on the periphery, so on the codecs, and these codecs here I'm talking about, it could be the host audio interface, it could be a digital analog converter, it could be some other, like a DSP or something like that. But these codecs, they are external to the A2B system. And these codecs, they're either going to be sending data, so at the top I have the RX side of the A2B, and at the bottom maybe the A2B is pushing data into some other codec. And here I have just kind of colored the audio samples. Here I'm supposing that I'm sending 4 channels of audio every sample period. And here you can see, for example, I take the first 2 channels that I receive on the main node, if you suppose the main node is on the left, and I'm going to insert those into the control frame, which is the first part of the superframe. And then I'm going to start pushing those downstream to the subordinate nodes, and they are going to maybe do something with it. And all of this is configurable. So here what I do is I say, all right, the first subnode is actually going to play back that blue sample 1 that we got on the main node. out onto its TDM interface, which might go into a DSP or something. And it's going to do the same for 2, but in the case of the blue sample, it's going to delete that from the superframe and then push the superframe further down. So you can see then in the superframe that's received on the second subordinate node, it's pretty much the same, except it's missing the blue part, because I can delete it. And accordingly, you can also push data from the last subnode, let's say this purple sample, and put it in the response frame. And then the response frame is then pushing that back up the bus, and I'm saying, okay, play that back also on the TDM interfaces of the first subnode and the main node. And yeah, you don't have infinite flexibility, but ADI, they designed it in a way which I think achieves basically everything that you would realistically want to do in an audio application. So yeah, kudos. Okay, so yeah, some of this is what I said already. One of the things that you need to take care of is that in this design, whenever you change this internal structure of the A2B fabric, whenever you decide that I'm going to insert more, whenever I decide I'm going to insert more samples or fewer samples or move samples, there's going to be more or less bandwidth between the nodes. And the bandwidth between the nodes has to be constantly updated. So whenever you change the level of bandwidth, you also have this response cycles setting that you need to also update inside each of the subordinate nodes. The reason for this was not entirely clear to me in the beginning, but pretty much it's because these chips actually, they are quite good at reporting errors. They can also localize errors. So they can say, for example, hey, I'm subordinate node 3, and you have a problem between 3 and 4. And then as the host, you can kind of diagnose this situation. ADI, they have lots of flowcharts in their documentation how to diagnose this. But one of the most crucial errors would be a bus drop, if you actually physically disconnect node 4 from node 3. And the way that that's actually detected is based on this response cycle setting. So it's actually telling the node, if the downstream node doesn't respond in time, then it's up to you to generate the response frame so that the rest of the audio system can continue synchronous playback without dropouts and pops and cracks and things like that. Yeah. So, yeah, I mean, I never really looked at ADI's vendor driver because it's copyright and can't really use that for Linux. But their reference manual is splendid. It really explains everything. So I took a look at it and then kind of thought, okay, well, what are the priorities, particularly for this shape use case that I was describing earlier, this weird product on the wall. There were some things to kind of consider in building a driver model for this. So one thing is that actually the bus is dynamic. So although it's not really emphasized by ADI, you do intrinsically have inside the hardware some form of not exactly hot plug detection, but you can detect when things are unplugged. And out of band, you can, in principle, detect when things are replugged. And there's a discovery algorithm that you perform in order to find the nodes that have been attached to your system. So in principle, you can actually take one node out and put another node in. And I thought, well, okay, that's not exactly a use case. My boss said don't work on it. But in a way, it kind of fits into the driver model quite nicely. So I thought, okay, that's one thing that we should consider. So yeah, after kind of reading about this, there's this concept of bus drivers, which, yeah, having not been in the kernel like too long, I had never really read a bus driver. I wasn't really sure what it is, but in my kind of canned explanation is this glue code which marries devices with drivers themselves. So I thought, okay, let's give it a go. Let's try and write a bus driver for that. One of the things which became quite apparent early on is that the topology of this bus, I don't know of any other bus which is quite like this except USB, where you have this kind of requirement that in order to discover something downstream, you need to have first enumerated the thing upstream. You cannot, in the A2B system, talk with the node n until you have set up node n minus 1. That's just a physical limitation of the design. So yeah, I have made some attempts there. They can be they can be debated. I'll put a link in the end of the slides for those of you who want to check out the V1 of the patch set. Yeah, other considerations. I wanted the superframe data structure that I showed you earlier with all these colors and arrows. I wanted this to be configurable at runtime. because essentially the hardware allows you to do it at runtime, so why not? Those of you who worked with ASOC, with the sound, you're familiar with K controls, so I thought, okay, let's just model these things as K controls. Let the user just set the thing up and then start playing audio. Another thing is also that reading some at the time confidential, now public documentation from ADI, their newer chips don't only support I2C as a control interface, they also support SPI. And I guess maybe they'll support some other stuff in the future. So one concern was also to separate the interface level from the kind of register access itself, hence regmap and all of those nice abstractions that we have in the kernel. And then you have these peripheral functions like codec and I2C adapter and stuff, which, yeah, I mean, these things also, they belong in their own subsystem, right? You don't want to make this monolithic driver for the whole thing. It also gets kind of hairy. Yeah, so in the end, what you get is, you know, you get your GPIO chip, you get your I2C adapter if you want it. All of these things come up as discrete devices inside the system. And then, of course, through your I2C adapter, then you can start enumerating any other I2C devices you have connected downstream. So now I'm going to talk a little bit about the details of the driver. I think most of the things I will say are kind of okay. Maybe some things you disagree with. If you strongly disagree with it, then raise your hand so I know to talk with you afterwards. Yeah, so first thing is just this interface driver, which kind of doesn't really concern itself about the specifics of A2B. All it knows is that, hey, I have this chip, and I need to offer some read and write access according to the kind of size of the registers inside the register map of these things. And I also need to provide this I2C transfer callback, which, if you go back to this diagram I showed you before about the two I2C addresses that the main node responds on, intrinsically, if you want to speak with the I2C target, which is on one of the subordinate nodes I2C segments, the address is going to be something arbitrary. So there has to be some rewriting of the I2C message when transmitting that to the, well, yeah, if you have an I2C adapter and then you say, let's talk to a device at 50, then you cannot just push that into the I2C segment on which the main node is on. You've got to rewrite it to this 69 that I showed you earlier. So it's just kind of doing this. And then there's this demultiplexing of IRQ signals, because each node can send its own interrupts, and these get coalesced in some registers inside the main node. And you basically just have to kind of poll or DQ the interrupts based on some status registers and say, okay, this interrupt is for the main node, this one is for the subordinate node, 3, then 4, and so on and so forth. Yeah, and this whole thing, I mean, basically, I said, okay, just have the interface driver register a class device representing the bus itself, and then register the main node itself. But the main node itself is going to be the actual node functionality will be controlled by a discrete driver of type module A2B driver, because actually I want to use the same driver for controlling my subordinate nodes as well. So yeah, that thing, the node driver itself, is actually what's going to be concerned with kind of bootstrapping the chip or registering the peripheral functions. And crucially, it also has to provide some callbacks for these sort of bus level operations. So one thing is to, when you want to change the data structure of this superframe that I showed you before, then it's a responsibility of the node driver to offer this to the core of the A2B driver model. And also the discovery process, main nodes, they also have to offer a way of actually triggering a discovery packet to be sent downstream. And they will also raise an interrupt when something has been or has not been discovered. So the node driver is just kind of exposing these features as well. And crucially also the response cycles, they also need to be configured. But these kind of functions, they just get exposed to the bus core, which I think is on the next slide. And this core code is responsible for performing this discovery algorithm that ADI prescribes for setting up your bus, and crucially for synchronizing the application of the data structure of the superframe. Because if the nodes themselves don't agree what is the data structure, then you're going to start having some weird bus errors, CRC errors, CRC checks will fail. You might even get nodes dropping off the bus even though they are actually physically connected because nodes did not respond in time because you didn't update the response cycles synchronously. So the core is also handling these more kind of hairy parts of the system so that the lower level like node driver doesn't actually need to care so much. And yeah, here also is whenever there's a bus error, this just gets reported to the core, and then the core can decide like what it's going to do. Is it going to say, oh, I had a bus drop, and then actually kind of, you know, unbind or remove the device inside the Linux driver model? Yeah, it has to decide. Yeah, and basically just the whole point is to separate some concerns. So it's also easy if ADI now come out with a even newer chip, then there is some function of that chip which requires its own new driver in a separate subsystem. Then the core offers some kind of general abstractions which allow you to kind of write that driver in an ergonomic way. So yeah, these are currently the drivers, codec, GPIO, clock, and I2C adapter. These are the kind of functional properties of the chip, and these have their own discrete driver which can be used. Yeah. So I mean, when you have a lot of these, like in the shape, then it gets kind of the number of devices and things you get gets kind of ridiculous. But here, I hope you can kind of see topologically like what I've been talking about the last 5 minutes. So on the top level, you have your I2C device on the I2C adapter, which is connected to your main node, and this will bind to the interface driver. The interface driver will register a class device representing the bus. It's my first A2B bus, so I'll just call that A2B0. And then this bus, it has some nodes on it. It will always have the main node, so that has ID 0. And that's this A2B 0.0 up there. And then, well, in a way, maybe it's a bit arbitrary, but it was convenient in terms of using the APIs of the Linux driver core to actually have these subordinate nodes be, or for any node n to be a parent of node n-1. So you get this kind of nested chain of A2Bs. So here I just have an example with a main node and 2 subordinate nodes. And then each one, it also has as a child device the functional features that it has. So all of them, they have codecs. On one of them, I'm also using GPIO, and one I'm using clock. Yeah. So this thing about configuring the layout of the superframe, what TDM slots, what audio samples are going to go where. It's actually, yeah, although it's the responsibility of the core to kind of do this in a synchronous way, or rather in an atomic way, the place where this is actually going to get configured is inside the codec driver itself. Because, yeah, it's a kind of feature of sound, right? It's not a GPIO thing. And K controls are a useful and kind of standard way to expose this to a user. So for those of you who are not so familiar with the sound subsystem in Linux, when you have a sound card, just as if you had any kind of physical audio device, you end up having like lots of buttons and switches and knobs where you can change things at runtime. And Linux sound cards, they're actually kind of like that as well. For any sound card, you can actually inspect using a mixer or other tools from AlsaLib. You can actually check what virtual widgets or actually virtual controls you have on the sound card. And you can change these at runtime, and of course, they will have some effect, but kind of curiously, I have not really seen this in other parts of the kernel, but it's one of those cases where there is no sort of fully generic user space API for this thing. That is to say, if you go to NetDev, for example, then when you want to add something new, they're going to say, okay, add a generic API, don't add a vendor API. But K controls arguably are something like a vendor API in the sense that they are wildly different. They really depend on the hardware that you have, what physical codecs, digital analog converters, ADCs, whatever junk you have inside your sound card. all of these will, expose to the user K controls, which the user can start fiddling with. And although there is, generally some consistency in this thing, they are just identified by strings, right? And you, as a user, kind of need to know your sound card. You need to know your hardware. I find that kind of funny. But anyway, that is good for me because I have this super weird sound card with millions of controls and millions of ways of routing audio data. So yeah, why not add the K controls? And yeah, pretty much the compromise I made, because it's difficult to synchronize operations between discrete drivers. In the sound card, I mean, you have these two callbacks like hardware params and hardware free, which from a layman perspective, you can think like when I open the sound card and declare that I'm going to play a file into it, there are some format parameters and bit rate and things like that, which or sample rate that you want to inform the sound card about so that it can kind of prepare itself. And in the driver model of Linux, that means that each codec inside your sound card is going to get its hardware params callback invoked. And when the user is done, when the user doesn't want to use those settings anymore, then you will also get this hardware-free callback invoked. So I kind of have a guarantee that if all of these codecs that you see here, if all of the codecs inside my A2B system are registered into the same sound card, then I'm going to get, not necessarily in order, but eventually I will get all the hardware params called, and that's the moment where then I can apply whatever structure has been set in these K controls. Or in the case of free, I can de-apply it and reduce data activity on the A2B bus, and that actually saves some marginal amount of power as well. Okay, yeah, I don't know how I am for time. I'm just going to keep talking a little bit fast and then open to questions. So yeah, one thing is that if you work with embedded Linux on ARM with sound, then you're going to be doing a lot of device tree, like the ASOC, which is ALSA system on chip. That's the kind of embedded audio subsystem of Linux. Is using a lot of device tree. It's heavily device tree based, and yeah, everything we use is basically device tree. So it kind of made sense. But specific to this shape setup, it actually causes quite a lot of problems because normally when you have something in your device tree, it's sort of expected to be there. And also ASOC, when you tell ASOC, hey, there's this sound card, it's composed of these codecs, 1, 2, 3, 4, etc., then ASOC also kind of expects those codecs to be there. And if even one of them is not, then the sound card will not register. So this combined with some more kind of core infrastructure in the kernel, like firmware devlink on, which I think is great and actually kind of educated me a lot in the things that I was doing wrong and which maybe I'm still doing wrong a little bit. But yeah, there were a lot of headaches and hair pulling, like trying to get this thing to work so that we could put this thing on the market in time, because yeah, otherwise the company will not be happy. Right, so yeah, this is just a quick diagram to show you what this shape system looks like. So it's composed of 3 types of tile. You have one and only one Linux box, which the product's called BioConnect Core. I don't know why. And then you have these BioSound shapes, which are actually basically amplifier units. They contain also a DSP and a microcontroller, and they also have an A2B chip inside. And that means that you can daisy chain these shapes together and form an A2B bus. And separately from the amplifier unit, it also has some analog output, and that goes into up to 4 passive speaker tiles, which are just, yeah, passive speaker drivers. And yeah, you can kind of tessellate this into a stylish design, and that's all great, but if you don't have 10 of these things, 10 of these BioSound shapes, then the device tree that I shipped to the customer is lying. It's not actually representative of the hardware. There's a deficiency, maybe you only have 1 of these shapes. That's actually a typical setup. So I had to do some kind of like smooshing and like ramming of things into ASOC to make things work a little bit better, and that's still somewhat of a work in progress. But it's, I would say, like somewhat independent of the stuff that's been submitted to the mailing list right now. I haven't put the sound card there because I think the sound card itself can be improved. But yeah, it exposes some weird things which I really need to talk with somebody about. So that's kind of why why I'm giving this talk, to kind of raise awareness of my problems. So yeah, I'm nearly done. Just a few other points of discussion, because I can really go on forever about this. One thing I find interesting for the sound guy up there is these K controls that I expose. If you know that there's actually no audio flowing from, for instance, one of your subordinate nodes down into whatever codecs that it's attached to, then from the point of view of the DAPM graph, which for the uninitiated is basically just a graph representing the power state of all of the discrete components inside the sound card. In this graph, you can mark things as, you know, whether they are on or not. And if they're not on, then this DAPM feature of the sound subsystem will automatically invoke the relevant callbacks of the driver of that codec to switch it off and save power, which, yeah, for people like us at B&O, it's important because we want to make use of that as much as possible and have good power management. It's actually a regulatory requirement. So I'm kind of interested in mapping the sort of state of the A2B superframe structure to the power state of the downstream codecs, because if you're not putting data into them, then they probably don't need to be powered. There's another thing, which is that this shape I mentioned, it has a microcontroller, and that microcontroller actually needs firmware update. And when you update the firmware, then it needs to be reset. And when you reset it, then it resets a regulator which supplies the A2B transceiver on that shape. Meaning that if you take the first shape here, if I update the microcontroller and reset it, then actually I get a bus drop error. It falls off the bus. And then I need to restart the discovery process and re-enumerate it. And then I need to go to the second shape and do the same thing. And yeah, if you represent this microcontroller as its own separate device, which you can, because it's just a device which responds on I2C, but independent of the node driver that I talked about before, what you will end up is that very quickly you will enumerate the whole A2B bus, you'll find all the nodes, but then in a somewhat random order, these nodes will start dropping off the bus as the driver that binds to the microcontroller loads the firmware, resets the microcontroller, and so on and so forth. So in order to kind of solve that problem, I introduced also some APIs to allow you to make a custom node driver, and BioSound Shape has its own custom node driver to kind of show off what the idea behind that is. Nodes not already present, I talked about that before. Then there's a whole other story about A2B muxes and USB alt modes, because our hardware team is kind of going crazy with A2B now, and they want to put it everywhere. And of course, then it introduces all of these kind of interdependencies between devices, and I'm kind of looking for, kind of trying to look into the distance, making sure that what I have done now is going to allow us to also model this kind of hardware in the future. And finally, I talked about device tree, but in principle, you might not describe this stuff using device tree, right? It would be great if you could kind of auto-probe, just like with USB, to check out, hey, I found an A2B node. What device type are you? What board type are you? Give me your vendor ID, product ID, and I will find the right driver for you. And maybe in that case, you don't need any OF firmware. ADI actually prescribes an EEPROM format with exactly that thing, but I found out yesterday from my hardware engineer who talked with ADI about it. They actually said, no, we don't assign vendor IDs. The vendor ID must always be our vendor ID. And the product ID must match the product ID found in the chip, the A2B chip, which is kind of self-defeating. I mean, why do you even have that information in the EEPROM? But let's see, maybe we can persuade them that this is a cool idea and to actually start assigning these vendor IDs. And then in that case, maybe this A2B code can also be extended so that you don't just have device tree as a requirement to describe it. Of course, ACPI is another story, but I don't know much about that. Yes, okay. So there's this link here. I actually don't know, maybe just take a picture of it or just go on law and search analog devices. Yeah, sure, I can do that, yeah. I just want to say, yeah, thanks to you for listening. Thanks to Emil Svensson, one of my colleagues who really helped me along with this and was very valuable to ping pong ideas off. My employer for giving me cool problems, Bang & Olufsen. We're also hiring, you see down here. And ADI, because they have amazing hardware, amazing documentation. Yeah, I'll leave it at that. Yeah, thank you.
Thanks. So I have a couple of questions.
Yeah,
so,
please. Yeah.
It was not really clear to me, but in your A2B bus, did you implement that as a specific other thing that drivers are needed for, or are you implementing like a GPIO expander or an I2C expander and using the Linux kernel frameworks that exist?
Yes,
for it?
yes. So for instance, the GPIO driver that I mentioned for the node, it just registers a GPIO chip with the GPIO with GPIO.
And then you can daisy chain anything else on that, like I2C on GPIO.
Yes. So the I2C controller also registers an I2C adapter, right?
Yeah.
So in this sense, everything, both internally in the A2B silicon and also everything behind the I2C, everything is a first-class citizen in the driver model, in the device model. So yeah, that was kind of the goal, right? Not to have this kind of opaqueness in the design.
Thanks. Yeah.
Oh, yeah. They also must go offline, yes, by definition of the hardware. So the question was, if one of the nodes drops off, what happens to the nodes connected downstream? Yeah, they also go away. You have to assume that, because there's no way of talking to them. And that's actually, just to add a few gory details, maybe actually that's a good question to ask the audience. Okay, in that event, so each of these nodes has a struct device associated with it. If I now pull that device out, that is to say, the physical device, if I disconnect it, should I call device unregistered? Should I actually destroy the struct device?
Depends, you are guaranteeing each node to be produced one, right?
Yes.
If one goes away, that's the variant going away, drop reference count, and everything is going to drop down to unregistering everything.
Unbinding, yes, but actually unregistering the struct device from the...
That drops, that's the variant of the entire chain behind.
Right, so do you expect device... Right, so do you expect device del to get called on that struct device?
Well, yeah, because it's going to release child, right?
Yeah, me too. But if you use device tree, then you will end up with lots of nasty problems because of firmware devlink.
Well,
And
I have a question about that.
yeah. Ask your question. Oh, throw the thing, but yeah.
So I got very confused with the device tree requirements you have.
Yes.
Because it seems that from the I understood your bus from the main node. It seems that you have the ability to enumerate all the nodes that are on that chain.
Yes.
So why do you need to describe them in device tree? You just need one entry for the main node, and that's it.
Because there are other resources that the nodes might need. There are firmware properties.
Oh, like the codec and GPIO on each node, you cannot detect that automatically? That's what the device tree is describing?
Yeah, I mean, the problem goes as simple as, for example, if the B-side transceiver of a particular node, it could be deep down, it could be node 5 or something like that. If the signal is inverted, for example, then that's a kind of firmware property, right? Or not a firmware property, but it's a description of the hardware which is required in order to continue discovering after that node. So that's an example of something that you put inside the device tree.
Oh, because that property, you cannot detect it automatically by probing?
No.
Okay.
No. There are a lot of properties which cannot be detected automatically. Moreover, because you have also a codec there, and that codec has to be glued into a sound card with a bunch of other codecs, some of which might not even reside on the A2B bus itself. All of those other codecs and all of the device driver infrastructure for ASOC, the embedded sound subsystem, assumes that you're using device tree. So you have to connect that thing using device tree, or at least that's the way that we are doing it. And I think to not do it that way, there are ways, but it's a huge pain in the neck to do that.
This is solved by the reading prompt part. So if you have configuration within the device itself, So you can read it per two, then enumerate.
In principle, yes. In principle, yes. But you would then still have the issue that you have a bunch of other devices behind the I2C adapter on some subordinate node, which from an embedded ARM perspective, you want to describe those with device tree, right? You don't want some firmware blob in some proprietary way to describe like all of that hardware, because, okay, the shape is kind of, the setup I described is pretty simple, but the stuff that we have inside the company, like some of our boards, there's like tons of stuff behind there. Yeah.
Is the EEPROM per node, or is it single EEPROM for all the nodes?
So the first thing is that the EEPROM is not a requirement. It's just basically a kind of pro tip from analog devices that you can put an EEPROM there, and then, although it's in their technical reference manual, it would appear from recent conversations with them that the whole purpose of this thing is actually to be passed by the vendor code that they ship to customers. It's not really used as a kind of canonical board identification system.
Right.
Evidenced by the fact that ADI actually told us that we can't have our own vendor ID, right? So, and moreover, that shape that I described, it doesn't even have an EEPROM. The hardware design is from some 5 years ago.
I was just coming to the device tree topic.
Sure,
If you had EEPROM
Yes.
per node, so
Yes.
to say, the EEPROM could have parameters that would lead to further self-discovery for the, let's say, following nodes.
Yes, and from an
And-
A2B perspective, I think that's a manageable situation. The problem is that I still want to describe the whole device structure underneath the I2C adapter using device tree.
And does the I2C main node have a visibility of all the other I2C devices that are existing on the bus? Or is it just visible to the next device, and the next device is then visible to the other device?
Maybe if we go to the diagram, you can point at what you are referring to.
Yeah, so let's say you have the main node.
Yes.
That main node I2C already sees the subordinate 1, but does it also see subordinate 10 if it is connected and up and running?
So the I2C itself is just, in the main node, it runs in target mode. It's a, or I2C slave, if you like, right? And then you have this.
That should be the master, or let's say primary. And then these ones. So if you have, let's say, address translations on the subordinates,
Yes.
then primary to secondary translation, which makes this a primary, and then talks to a secondary. I'm just trying to understand how the I2C, let's say, layout would look like in such a case. So here you have multiple targets on the controller. So,
Yes.
so let's say the main node has hex 69
Yes.
as the address.
Yes.
That would convert, that would send the data to the subordinate node 1,
Yes.
which will then, which will then expose subordinate 2 as probably an extension of hex 70 or hex 71, whatever address might be allocated.
No, it doesn't work that way.
No?
The reason being that there's only one I2C interface, and that I2C interface is always in target mode on the main node, and always a controller on the subordinate nodes. Meaning that there is actually, it doesn't make sense to talk about the subordinate node having a I2C address.
Okay.
Or parentheses, there is a way, but this is used for some mailbox feature for board-to-board communication, which I think is not.
So there
not
is
relevant
no
here.
chance that one device will keep holding the data line?
No. So if you mean indefinite clock stretching, for
Yeah.
example,
Yeah.
no, there's a built-in timeout inside the chip, such that when it's functioning in main mode, it will release the SCL line after so many cycles, so many microseconds.
So that was actually one of my questions earlier, that this looks very much like an I2C expander, that you write in one register
Yeah.
what the next OX69 will address. So it's actually,
Yes.
you're switching in the OX68 which of the subordinates you are using. But then you could also, if you have an EEPROM on each subordinate node, you could use that and read from those and get, this subordinate node is X or
Yes,
Y.
yes. The problem I have with that is, besides the remarks I made about device tree being kind of canonical elsewhere in the system already,
Yeah.
another problem there is that there is no standard for actually identifying the node, right?
No, but-
ADI gave this very disappointing answer. So I was hoping to come and actually say, hey guys, we can do this, but now I'm actually not sure if we can do that.
I think
That's-
that would be possible for you to say, because it's your system. ADI, yeah.
For sure.
They might have something in their system, but
All right, but
Yeah.
you see, if I want this in the main line, I cannot just declare, here is Bang & Olufsen's system of identification, take it or leave it, right?
no, that would be the Linux system. So
Sure,
you will be
sure,
the
sure.
vendor authority and
that
give
would be-
vendor IDs to everybody
Yeah.
from Linux.
Yeah, but like adding EPROMs, that's expensive and some trouble putting it on in the hardware.
Yeah.
They're paid for the hardware.
Oh,
EEPROM is the least of our worries. Yeah.
he's just saying he's ready to pay for it.
So now that you are shipping Linux in one of these fancy speakers, if I go buy myself one of these, can I like get the sources and install my favorite media streaming thing on it and like put my own Linux in there?
You can get the GPL v2 sources, and we don't have any GPL v3. I think that answers your question.
Yeah, but I mean, like, is the platform is like hermetically sealed, or can I put my stuff in there?
I tried like for many days. It's pretty good.
All right.
You can't install your own software. It's using secure boot.
Okay, thanks.
Sorry. Yeah. Not my choice, by the way.
Well, you say like you're hiring. I mean, so what I want to know,
Yeah.
which you might guess I have like 1 or 2 speakers, is it like, do employees get like a discount? Because, I mean,
Okay.
it could actually make sense to do like a small jump, like for a couple of weeks, get some speakers and hard one.
Yeah. There is a discount.
And the property.
Right.
Could be worth it for a couple of 90s.
You can't afford them even with the discount.
Okay, so
Okay, I don't know how
think
that works, but yeah.
yeah.
I'm pretty sure I can. It's a qualified guess.
Right. I think we're come up to closing time. So I
I just want to hijack one
Yeah,
moment,
sure.
just to say, please talk to me about my problems. Like or check rather. I'm not going to repeat myself, but check out my patch set. Like I have some specific problems which I'm kind of not sure about, and I can't find information because it's like, I don't know. I'm tired of reading like dd.c and stuff like that and trying to figure it out for myself. So I want to talk with an expert and figure out what is the correct way to finish.
Chat GPT.
Pass. Yeah.
All right. So yeah.
Yeah, I'm done.
Thank you, Alvin.
Yeah, no problem.